Hello friends, I am repeating the presentation on students T distribution mainly to improve the video quality. The content is going to be more or less the same of my last video. In fact, I had produced two videos on student T distribution. I am just going to summarize the main point. The main rationale behind making this video was that I was not very satisfied with the video quality of the last two videos on student T distribution which I had uploaded earlier. And that was mainly because I had used a mobile camera to record the screen, and so there was some flickering in the recorded video. Now fortunately I know how to share the screen using screen recorder, so I'm just repeating the main points. I hope it will be more easier to read from this presentation than from the earlier presentation. The content remains more or less the same. So I'll briefly revisit the history. Student T distribution is a continuous probability distribution. I had told you that, and it has a probability density, and it is actually a family of probability distribution. That means it is not one specific distribution, but there is a number of probability distributions that are different forms of the student T distribution, and that is determined by a parameter called degrees of freedom. So student T distribution, the main parameter is the degrees of freedom. That is something I will revisit here in this video as well. As far as the history of this distribution is concerned, this distribution was invented by a statistician named William Cecil Gossett, who worked in a brewery in Dublin. He seems to have been interested regarding the regarding hypothesis testing regarding the mean of based on very small samples. So based on that, he had derived this distribution, and he had published in his work on students T distribution in the 1908 paper in Biometrica. And since he had used the pseudonym student, so it derives its name as students distribution. Actually, this name was attributed later by the famous statistician Professor Ronald Fisher, who worked on and extended the work of Gossett further. Now coming quickly to the main point. So I have got x1, x2, xn IID, independent and identically distributed random variables from a normal distribution, mu and sigma. Both I don't know. Now my aim is to estimate or test a hypothesis regarding the population mean without knowing what sigma is. So I look at this ratio x bar minus mu s by root over n. So this root over n would come in the numerator, and it would be root over n times x bar mu minus mu by s. Then the distribution of this ratio turns out to be the students T distribution with n minus 1 degree of freedom. Now if you knew the value of sigma, suppose I change the problem. If x1, x2, xn were IID n mu 1, so suppose sigma is 1, then we don't need student T distribution, because in that case x bar minus mu divided by s into root n, this quantity will follow standard normal. So if you know sigma and then this ratio, then use this ratio with sigma in the denominator, and this ratio will follow standard normal distribution, because the distribution of x bar will be if x1, x2, xn are IID normal, then the distribution of x bar will also be normal with mean mu. Variance would be sigma square by n. So that would be just a standardization. So this would, by that logic, it will be n01. So when sigma is known, this ratio is standard normal. But when sigma is not known, we replace sigma by an estimator. So that estimator is the sample variance. Only here, instead of 1 by n, I am taking n minus 1 in the denominator. So if you replace sigma by the sample standard deviation, or to be more precise, the bias corrected standard deviation, then this ratio of sample mean centered divided by the sample standard deviation into root n, that turns out to be student T distribution. Now, what is meant by degree of freedom? So let us look at the formula for the probability density function. I told you that student t distribution is a continuous probability distribution or a family of continuous distributions. So it has a density, and the density function formula is written over here as this part is a constant, and this is the variable. So for every t is a real number, any real number, so the value of the density is 1 plus t square by mu raised to the power minus mu plus 1 by 2. This is of course not a probability. You know that a density function is a non-negative valued function in integrating which you compute probability. So this does not give, this formula does not give you a probability, but integrating this formula you get probability assigned by student t distribution. Now if you forget for this constant, just ignore this constant for a moment and pay attention to this formula, then this is looks quite simple. This is just 1 plus t square divided by mu raised to the power mu plus 1 by 2. Now mu is called the degree of freedom, and it determines the parameter properties and shape of the student t distribution. And here these are gamma functions. I hope you know gamma and beta functions. So gamma of half is square root of pi, and gamma of any n is n minus 1 factorial, and gamma function is computed as integral 0 to infinity e to the power minus x to the power n minus 1 dx. So that is gamma n. So the constant is the gamma function, and here by changing the values of mu we get different student t distribution. Like in the earlier paragraph, it is said that x bar minus mu s by root over n is following student t distribution with n minus 1 degree of freedom. So you got to put n minus 1 here. So what would be the formula? 1 plus t square by n minus 1 raised to the power minus n by 2, because n minus 1 plus 1. So that would be 1 plus t square by 2 t square by n minus 1 raised to the power minus n by 2. That would be the formula for the student t distribution with n minus 1 degree of freedom. And of course here you will have gamma n by 2, here you will have gamma n minus 1 by 2, and so on. Now what is the role played by mu? Now for smaller values of mu, this has heavier tails. That means for smaller values of mu, lesser and lesser moments will exist. So for mu equal to 1, that is the extreme case, you have something called the student it would be for mu equal to 1, it will be the standard Cauchy. What will be the formula? 1 plus t square raised to the power minus 1. So here I will show you in under the special cases. So here this is the special case. For mu equal to 1, this is the formula. T is any real number. So this is called the Cauchy distribution. And if I now let mu increase, so the for mu tends to infinity, this is mu equal to infinity is just a symbol, then take the limit, it turns out to be standard normal. So Cauchy and standard normal are the two extremes of the student t distribution. And by the way, just like you can see standard normal and Cauchy, this is a symmetric distribution because f of t is equal to f of minus t. If I put f of minus t here, so t squared will be square out the negative. So f of minus t is equal to ft. So this is a symmetric distribution. So student t is a symmetric continuous distribution, and the parameter is the degree of freedom. Now why is this distribution so important? Because in the context of testing of hypothesis, suppose we are faced with this problem that x1, x2, xn are IID normal with mean mu and variance unknown. Mean we don't know. I am testing a null hypothesis mu equal to mu naught. Again sigma not equal to mu not equal to mu naught. And I don't want to make any statement or estimate the sigma. Then how do I test this hypothesis? So we have seen that to test a hypothesis I need a test statistic, and how the test statistic should be chosen. Ideally a test statistic should be one for which you know the distribution of the test statistic under null hypothesis. So I have already mentioned that when you don't know sigma, you know that x bar minus mu s by root over n, this follows student t with n minus 1 distribution. So under the null hypothesis, mu is equal to mu naught, we could use x bar minus mu naught s by root over n, that as the test statistic. Then this will follow student t distribution with n minus 1 distribution degrees of freedom. So we have a sampling distribution to test this null hypothesis. We can compute the critical region. So you know that a Wald type test would give you a two-sided critical region. So I would ask you to revisit the notes and the lecture on the testing of hypothesis, how to construct critical region and the p-value. But the main point is that the student's t distribution became famous because it is the sampling distribution of the test statistic for testing mu equal to mu naught against a two-sided alternative when the population variance is not known. So remember, student's t distribution is used as a sampling distribution for testing hypothesis regarding the population mean when the variance is not known.